Okay, so we're going to make use of iteration now. We're going to make use of loops. And so remember, we've got repeat until loops, while and while loops, which are for indefinite iteration. And then we have for loops for definite iteration. Now, in this case, what we're actually going to be doing is we're going to be having a look at this trace table. And this trace table is going to be of the variable total size, data to be sent, and number of packets. Data table is very common. And so it's not asking you to do the code right now. It's asking you to see if you understand the code. Now, constant payload size 250. Why is that constant? Well, it can either be a constant or a variable. The clue is in the name. Constant payload size, that means that it's always 250. You can't change it. If you remove the constant, it becomes a variable and you could change the size. So you use constants for values where you're not going to change the value associated with it. Okay, so we've got payload sizes 250, header size is 50. And FYI, that's why it's not going to be in a trace table, because it's not going to change. You only trace the variables. Okay, output. Enter the number of bits of data to be sent. Data to be sent, user input. So that person's put in 750. So that's where that came from. Total size is payload size plus header size. Payload size is 250 and header size is 50. So 250 plus 50 means that total size is going to be 300. Ooh, yeah, that's pretty clear, 300. Okay. Okay, what's next? Number of packets becomes 0. So in here, I'm going to put 0. Now, you might have wondered, why didn't I write it here? In theory, you should always read left to right in rows like this. I don't need to change that to 750 because it hasn't changed. You only need to change a trace table if the value changes. Okay, next thing, repeat. Data to be sent is data to be sent minus total size. So data to be sent is 750. Take away total size, which is 300. So 750, take away 300 is 450. And then we sign it back. So then that becomes 450. And remember, we're in a repeat. So it's repeating until something happens. Next is number of packets is the number of packets plus 1. The number of packets was 0 plus 1. 0 plus 1 is 1. Restore it back in there. So that becomes 1. What's next? Until the data to be sent is less than or equal to 0. Data to be sent is 450, so it's going to come back to this point here. Data to be sent is data to be sent minus total size, so 450 minus 300, so that's become 150. What's next? Number of packets is number of packets plus 1. Number of packets is 1 plus 1. 1 plus 1 is 2. Is the data to be sent less than or equal to 0? Nope, it's 150. So we come back here again. Data to be sent is data to be sent minus total size. So 150 take away total size, which is 350. 150 take away 300 is going to be minus 150. And then number of packets, which is 2 plus 1. So 3 is the number of packets. The number of packets is 3. Data to be sent less than or equal to 0. Yes, it is. Algorithm finishes because there's nothing else here. State why both payload size and header size from the algorithm did not need to be included in the trace table. What was I? To be consistent, I was using blue. So I would say something along the lines of these a trace table. These are constants, and therefore the value won't change. These are constants, so the value won't change. So what would be the point of tracing them if they stayed the same? Okay. Shaded one lozenge to show which of the following best represents the input and output from the algorithm. So what are the inputs? So what is input? When the user enters the value 750. So the value 750 was the input for data to be sent. So input data to be sent. I think straight away we're in a pretty good place. And one of the outputs is certainly going to be probably the number of packets. Input the number of packets? No, that's something that we're generating as we're going along. And output the total size? No, total size was a set thing. And then input total size, no, we got this from here. It wasn't an input, it's something that we started with, and output was data to be sent. So I think input data to be sent because the user inputted that. So it's going to be that one. Onwards to the next one. Again, more problems making use of iteration. And now we're getting to the point now we're going to have to write some of our own code. An application allows only 2 users to log in. Okay. The usernames are stated in table 1. So the username Gower, and that's their password. Username Tough, that's their password. Develop an algorithm using pseudocode or a flowchart that authenticates the user. Now, authenticate means it's proof that you're who you say you are, so that the username and the password matches. The algorithm should, and so they decomposed it for us. That's very kind. Get the user to enter their username and password. Check that the combination of username and password is correct. And if so, output the string access granted. Get the user to keep re-entering their username and password until the combination is correct. Okay, so we'd use a for loop when we know how many times somebody would need to do a repetition. In this case, we need to keep repeating the loop until we get the answer. So that you can either use while or repeat. In this case, I think I'll repeat the algorithm. What do I need to do? Well, I need to ask the person to enter the username. So print. So this is a message for the end user. Please enter your username. And then we're going to store their uname, assign. And do you remember the function to get the input from the user? That's right. It's user input. The next thing is we're going to want to ask them to enter their password. Once you've asked them to enter the password, then you're also going to want them to store their answer in a variable. I'll call it p-word, same as before. Great. Now, I'm going to want to keep this going until I've got this match or this match. So until, now this will be a bit of a trickier one to write. I can't say until either username is Gower or Guff or password is this or this. I have to match them up. So I have to match the username to this and this. So this and this, or this and this. So let me write the first one. Let me narrate it. So uname is going to be the logical comparison equal, and then I can say Gower and p-word is again equal to, and they're not either of these, the one it matches up to, that one. So it's equal to, I'm putting these things here because I assume it's a string. So I have to write it. So 9F DG3. So it's this and this. And then what I would say is, inside parentheses, so it's that and that, or, and then I'd have to do the other combination it could be. So it's username equals, and so this time I need to look at that and that as a match. Be careful to write it so it's all case sensitive, and then it's and p-word equals, and remember it's going to be the one that matches it, so the one over there. Got to be a bit careful because you see I've put this and this inside the parentheses, so it's all of this together, or, and then I should do the same here, all of this and this in parentheses, in brackets, so that they're separated. This will keep running until either that combination or that combination is found, and then it should output access granted. So if I put down here, print, the only way you'll get to this line is if you actually terminated this loop, and this would only happen if you got a match, and I have to do the message exactly how they wanted. It was going to be access granted. Now, there would actually be other ways to do this as well, but that is certainly one of the ways you can solve this problem. Okay, this is a 9 marker, so quite a big question, but actually I don't think it's necessarily adding that much more complexity. It's just, longer, more broken up, but using all the same thinking as we did before. Again, it's going to be using iterations, so loops. In this one here, it says develop an algorithm using either pseudocode or a flowchart, so we'll be using pseudocode in our case, that helps an ice cream seller in a hot country calculate how many ice creams they are likely to sell on a particular day. Okay, so that's the goal of our algorithm. And we can now tackle it bullet point by bullet point. We can read through it all potentially, but it's really nice they've bullet pointed it for us. They've basically decomposed and abstracted the problem, which is great for us. Get the user to enter whether it's the weekend or a weekday. So, technically, I'm a bit anxious because I'm a bit low on space, but technically, I probably should ask the question, first of all, to ask them whether it's a weekend or a weekday. So let's try that. So I'm going to ask, is it a weekend? And I'm going to assume they're going to respond yes or no to that. Probably should validate, but it doesn't require it. And so then we'll store that inside a variable called week, and we'll put the assignment there. And do you remember what it is for a person to put an input, an end user? That's right, it's the command user input. And I'm assuming that this will be either, is it a weekend? Yes. So that'll store a yes. Is it a weekend? No. It'd be a weekday. Okay. Get the user to enter the temperature forecast in degrees Celsius. Okay. They should enter a number between 20 and 45, inclusive, i.e. it can be as low as 20 and as high as 45. If the number falls outside of this range, they should be made to re-enter another number until they enter a valid temperature. So we're going to need to repeatedly ask them until they get it right. So we can either use a while loop or repeat until. I think repeat works quite nicely here. So we can say repeat, and then we'll say, we'll get them to enter a temperature. So I'm going to ask the question to print a temperature. I'm anxious of running out of space, but probably it should say, it would be better if it said between 20 and 45. So please enter temperature between 20 and 45. And then we'll say temp, again, user input as before. So we're going to get the person to enter it in here. And remember, you want to keep looping around until something becomes true. In this case, until what? Well, until temp is greater than or equal to 20. Remember, this is one of the places you can go wrong. And temp, in fact, let's go wrong here just to prove the point. Temp is less than 45. Now, if you do this, what's going to happen is if you actually put 45, 45 is not less than 2045, so it would fail. So you'd have to say less than or equal to. Potentially you could say less than 46 if you're only putting whole numbers in. But if it's not just whole numbers, you could put 45.9 and it would be wrong. So I guess that's the trade-off. Okay, we're now in this bit here. So this looks like one of the more substantial bits of the algorithm. Calculate the number of ice creams that are likely to be sold using the following information. Okay, if it's 100 ice creams are likely to be sold if the temperature is between 20 and 30. Right. If it's between 31 and 38, it's 150 degrees. And if it's higher than 38, then it's 120. Okay, so what we could do is there's 3 different outcomes. Now, if there was 2 outcomes, we could use a selection statement of if and else. In this case, because there's 3, we should use if, else if, and else. So if what? Well, if we're checking if the temperature is between 20 and 30. Now, you can't put a number lower than 20, right? So we're saying if temp is between 20 and 30 inclusive. So if you said less than 30, right? you're not including 30. So again, you'd have to say less than or equal to 30. Well, then if it is, then what? Well, then why don't we initialize ice cream? So iCreams is going to be set to assign the value 100. And then else if, so what's the next thing we have to worry about? We have to worry about this one here, between 31 and 38. So we can say if temp, we've said if it's 30 or lower, it's already this. So now we can say if temp actually is less than or equal to 38, because remember it has to be inclusive of 38, then what do we do? Well, then we set iCreams now, instead of being equal to 100, what does it say it's going to be? Let's have a look over here. It's 150. So now we've got 150 ice creams. Now for the last one, you don't have to do else if temp is greater than 38. You can just say else. Why can you just say else? Well, because it's the last one left. So we can say else. I'm going to have to do something a bit silly here and write it up. I should write it down here, but I'm running low on space, which I'm a bit anxious about. So I'm going to write it up here. My apologies. It doesn't change the way the algorithm works. It just makes it look a bit ugly. In fact, gosh, the way I wrote that was pretty horrible as well. So iCreams, let's look at the last one here, is 120 if it's there. Oh, you'd have thought it would be higher again, but it's not. It's 120. Okay. Double the estimate if it's a weekend. So we'd have to say in here, if, oh, sugar, we should write here, and if, for all of this statement, oh, I'm really going to be low on space. So if what? If weekend, remember this is the thing we did right at the beginning, if weekend is equal to, so if it's the weekend, we should double it. So if weekend equals yes, then, did it say we had to double it? Yeah, I think it did. So we'd have to say in here, oh gosh, I'm going to zoom in to allow me to do this. If it looks a bit small, it's my apologies. I guess you can see it fine, but when we zoom out, we say iCreams, whoops, is assigned iCreams, and this time we times it by 2. And then we should, it should end if, but I'm out of space, because the last thing I need to do is actually output the number of ice creams that I'd like to be sold. So the very last message is print in this case, actually output, what's the message? We can just put in here, I probably should put a whole message, but I'm running low on space. So output iCreams. Apologies for going a bit ugly at the end. I had to sort of squeeze it in there. Okay, another pseudocode problem, similar kind of idea again. You can see that these all have a certain theme. Hopefully I won't have to squeeze it as much as last time. It's an 8 marker rather than a 9 marker, but it'd be pretty similar, I would imagine. Develop an algorithm using flowchart or pseudocode. It's for a taxi company to calculate a fare. So last time it was ice creams, this time it's a taxi fare. And again, very helpfully, they've broken it down for us. Prompt the user to enter the journey distance in kilometers. So I should actually prompt, so I should say, I keep writing print, maybe output's the right thing to say. I'm marking this, right? So if you put output or you put print, I know what you mean. So output, enter distance in kilometers. Now, I probably should have read on a bit more because it says that it has to be greater than 0 and the user should be made to re-enter until the distance is valid. So you don't know how many times they're going to get it right or wrong. So it's going to be indefinite again. So at the top, I'm going to put repeat. The person's going to enter it and I'll say, maybe I'll put down here, kilometers is the variable, user input, And I have to keep repeating this until the actual user input, until the kilometers is, in this case, positive. So until is greater than 0. So until kilometer is greater than 0. Brilliant. And it'll keep asking the question. I mean, it might be better. I said enter distance in kilometers should be greater than 0. But I'm a bit low on space. Prompt the user to enter the number of passengers. No validation required. So I can just ask the question and then take the value in. So for this problem here, I'm going to ask him how many passengers, and then I need to store that. I'll call it pass, and then assignment, and then user input. And then I've stored how many passengers there are into this one here. Okay, great. Calculate the taxi fare by charging £2 for every passenger regardless of the distance, and charging a further £1.50 for every kilometre regardless of how many passengers there are. Output the final taxi fare. So it's £2 times by pass plus £1.50 times by kilometres. So I'm going to use fare to calculate this whole thing. So fare is going to be assigned £2 for every passenger, regardless of distance. So that's going to be passenger times by £2. So let's say times by 2.00. In fact, it'd be good to put that in a bracket. Plus £1.50 for every kilometre. We've got how many passengers. So times by plus kilometre times by 1.50. I'll be honest with you guys, I really thought I was going to run a bit low more on space. And then so finally output, plenty of space in the end, output, and then you could output fare. And that'll be the calculation of the fare. I think it was a lot easier than the last one, to be honest. I guess it's 1 mark less. Okay, in this problem now, we're going to be making use of definite iteration. That's iteration when you know how many times it's going to go around. Typically, you do this with a for loop. In this problem here, we've got an algorithm shown in figure 4 and figure 5, and both have the same purpose. Remember, an algorithm is a set of instructions to achieve a goal, and both of figure 4 and 5 have the same goal. The operator left shift performs a binary shift to the left by the number indicated. Remember, if you go shift by 1, you double the number, shift by 2, you times it by 4, shift by 3, you times it by 8, and so on. For example, 6 left shift 1 will shift the number 6 by 1 place, which has the effect of multiplying the number 6 by 2, giving 12. Okay, and so here's 4. The other one is going to make use of a for loop to do it. Okay, complete the trace table for figure 4 when the initial value of number is 4. So number is 4, left shift by 2. So left shift by 1 will be timesing it by 2, but left shift by 2 is timesing it by 4. So result, first of all, is going to be number. So that's 4 times by, and then it will be times by 4. So it'll be 16. So the original one here is 16. So that's this value here. And then it's result minus number. And number is still going to be 4. So in this case, it will be 12. Okay. Complete the trace table for the algorithm shown in figure 5, when the initial value of number is 4. So on this one here, the first level is, it will say result is 0, and which is here. Then x is 1, and it'll be x will be 1, then it'll be 2, then it'll be 3, and then it'll be the end of the for loop. So x is 1, then it says result. Result is result, which is 0, plus number. So that will be 1. So result, oh, because number's not being input yet. Number's still 4. So result, which is 0, plus number, which is 4. So it will be 4. Okay, so what's next? Well, next is x becomes 2. So x is 2. And then it will be result, which was 4, plus 4. So it will be 8. and then it will be 3. And when it's 3, it's result plus number. So it's 8 plus 4. So it will be 12. Okay. Then it says state the purpose. Well, if you put in a 4, then it's the equivalent of timesing it by 3. And whatever number we put in, you are going to have it multiplied by 3. In this case, the first thing that happens is you times it by 4, and then because it will take a number away from itself, it will be times by 3, while the other one, it's 1 times the number, 2 times the number, 3 times the number. So the answer would be, in this case, multiply number by 3. Okay, and then it says, explain why the algorithm in figure 4, so this one, can be considered to be a more efficient algorithm than 5. Now, efficiency is where we've come up before. Do you remember we talked about binary search versus linear search, and that binary search is more efficient than linear search when there's a large number of items, because you don't have to have as many instructions. So you see here, it takes more instructions to find the answer using figure 5. So what's the answer? We write it out now. So we remember with an algorithm, the definition was a set of instructions to achieve a goal. Figure 4 requires less instructions to achieve the goal, and therefore is more efficient. Okay, we're now looking at arrays. And earlier we looked at strings, and we said that a string had an index and at position 0, 1, and 2. And in this case, we have an array, which is a collection of integers. Now, it's worth remembering that in an array, it also has an index, and that will be at position 0, position 1, position 2 inside that array. Okay, let's have a quick read. So, in this case, it says array indexing starts at 0, right? So 0, 1, 2, and you can assume that's always the case. There's an array called R, storing values 4, 1, and 6. So it's a one-dimensional size 3 array. Then there's a variable called sorted, set to false. It's saying in a while loop, so an indefinite loop, while sorted is still false, first set sorted to true, then set I to 0. While I is less than 2, then you can do a bunch of stuff inside here. All right, let's keep going. State the data type of the variable sorted. So sorted is set to false. We did something very similar to this right at the beginning. If you remember, that is a Boolean value. Okay. This one, I don't know if you recognize it, but it's saying if that one here is smaller than that one, if that one there is smaller than that one there, then create a temporary and essentially swap them over. I don't know if you remember, but that's actually a bubble sort. The identifier sorted is used in the algorithm shown in figure 2. So here, explain why this is a better choice than the identifier S. Brilliant. So this is a programming technique, same way why you'd want to indent the code. It makes it easier to understand what the code does, and for other people to understand what the functionality is as well, even yourself when you come back later. So let's write the answer. So sorted, the name of the variable, describes the purpose of the variable. Putting S wouldn't describe the purpose. That can mean anything. And that's going to make it easier to follow and understand, both for you when you come back and using it, or for somebody else to come back and using it. You should always have meaningful identifiers for variables, for arrays, for subroutines. Okay, the same algorithm from before. And remember, we said that this was actually going to be a bubble sort, which might be a bit of a giveaway. This time, we're going to have a trace table. But first of all, we've got to shade one lozenge to show which of the following contains the false statement about the algorithm. Okay. The algorithm used a name constant. Do you remember you have a constant versus a variable? There are no constants there, so that actually is false. But let's do the rest. The algorithm uses indefinite, so that while sorted, that's indefinite, iteration. So it does use it. The algorithm uses nested iteration. Brilliant. You see here, that's iteration, isn't it? And that while loop is nested inside. That if statement is nested inside the while loop. So that top one there, it does not have a constant. All right, this is the trace table. Let's get it done. So 416, so that's bit here. Sorted is false, so it's there. While sorted equals false. Sorted is false, so continue. Then the first thing that happens is that sorted becomes true on this line here. I becomes 0. While I is less than 2, 0 is less than 2. If array at position I plus 1. So remember, I is 0. So array at I plus 1 is going to be here. It's going to be the value 1. Is 1 less than array at 4? So is array at plus 1, so is 1 less than 4? Well, 1 is less than 4, so then t is r at I. So remember, I is 0, so array at position 0 is 4, so t becomes 4. I becomes, what's at r at I plus 1? So this is r at I, so it's 0. 0 plus 1 becomes 4. So that variable there gets put in here. So that's become 1. Array at position I plus 1. So remember, I is still 0 at plus 1. So at 1 becomes what's been held at t. So 4 gets put into that box there. So this is the swap that you get in the bubble. And then sorted, sorted becomes false. So that's switched back to being false. And the if, I is I plus 1. So I becomes 1. Great. And then m while, and so you come, but you don't go back to this while, you come back to the one that's indented at the same place, so back to here. Is I less than 2? Well, I is 1. Is 1 less than 2? Yes, it is. Is r, so I is 1, so 1 plus 1 is 2, so r at position 2, so 6. Is 6 less than 4? Is 6 less than 4? 6 is not less than 4, so you don't do any of that. And if I becomes 2. And then it says, m while, come back in here, is 2 less than 2? 2 is not less than 2, so that while loop stops, so I come back to here. Is sorted equal false? Sorted is still false. And so now it says sorted becomes true. So that becomes true. I becomes 0. While I is less than 2. Is 0 less than 2? Most definitely it is. Is r at I plus 1? So is 4 less than is 4 less than 1? Is 4 less than 1? No. So I becomes I plus 1. So that becomes 1. And then it will come back here. Is 1 less than 2? 1 is less than 2. I is 1, so is 4 less than 6? Sorry, is 6, is 6 less than 4? No, it's not. So we don't do any of that. I plus 1 becomes 2. Is 2 less than 2? No. So while loop terminates, come back here. Is sorted, while sorted is false. Is sorted false? No, sorted is true. And then it's going to end while. And you can see here what's happened is that it's become 1, 4, 6. So it's actually sorted the list.